Now please note that L'Hopital's rule can only be used if you end up with 0 over 0 or plus or minus infinity divided by plus or minus infinity when you do direct substitution. But there are other types of indeterminate form. If you end up with one of these other types of indeterminate forms, you have to do some work to get into 0 over 0 or infinity over infinity. For example, 0 times infinity is an indeterminate form. If you end up with 0 times infinity after direct substitution, you're going to have to manipulate yourself using algebra or a trig identity to get yourself into 0 over 0 or infinity over infinity. Another indeterminate form, infinity minus infinity. If you end up with infinity minus infinity after direct substitution, you're going to need to use algebra or a trig identity to get to 0 over 0 or infinity over infinity. 1 to the infinity is indeterminate form, 0 to the 0, and infinity to the 0. These 5 different things here, we're going to call these our bad indeterminate form. If we end up with these bad indeterminate forms, what we're going to have to do to evaluate the limit is manipulate it algebraically or using a trig identity, get it to be 0 over 0 or infinity over infinity, and then we can use L'Hopital's rule to evaluate it. When you deal with limits, you always start with direct substitution. If direct substitution gives you 0 over 0 or infinity over infinity, use L'Hopital's rule to evaluate the limit. If it gives you one of these bad indeterminate forms, 0 times infinity, infinity minus infinity, 1 to the infinity, 0 to the 0, and infinity to the 0, if it gives you one of those 5, you have to manipulate the limit algebraically or with a trig identity, end up with 0 over 0 or plus or minus infinity over plus or minus infinity, and then use L'Hopital's rule to evaluate. Please note that the following are not indeterminate forms. If you have infinity plus infinity, that's just equal to infinity. If you have infinity times infinity, that's also just equal to infinity. Infinity raised to the infinity is infinity. And a number that's not 0 over 0, well, that's just something that does not exist because it's undefined. So this is undefined, which means that limit does not exist. Or if it's a one-sided limit, you might want to look to see if it's approaching positive or negative infinity. Let's look at the following 5 examples where it's asking us to evaluate the limit using L'Hopital's rule if necessary. The very first thing we do with limits, no matter what we have, is we always try direct substitution. For number 4, we have the limit as x goes to 0 of e to the x minus 1 all over x. Direct substitution would give us e to the 0 minus 1 over 0, and that's just going to be 1 minus 1 or 0 over 0. This is indeterminate form. When you get indeterminate form, and the good indeterminate form like this, we use L'Hopital's rule. L'Hopital's rule, remember, said, in order to evaluate this limit, what you do is take the derivative of the numerator. Well, the derivative of e to the x minus 1 is just e to the x. You take the derivative of the denominator. Well, the derivative of x is just 1. And then you take the limit again. Well, this becomes the limit as x goes to 0 of just e to the x. If I plug in a 0, that's e to the 0 or 1. Therefore, this limit is equal to 1. What about example 5? I have the limit as x goes to infinity of the natural log of x to the 4th divided by x cubed. Now, anytime you have a natural log or a log, and you have something where the argument is being raised to a power, it's best to rewrite that using your properties of logs and then trying to take the limit. Recall that the natural log of a raised to the r is equal to r times the natural log of a. So we can rewrite this numerator as the limit as x goes to infinity of, instead of the natural log of x to the 4th, 4 will go and multiply the front. That's going to be 4 times the natural log of x, and then the denominator stays the same because we're only using our property to rewrite our log. Now that we've rewritten it, let's go ahead and do direct substitution. If I plug in an infinity in here, well, the natural log of infinity is just infinity. Infinity times 4 is still infinity. Infinity cubed is infinity. So this is indeterminate form. Whenever we get infinity over infinity, we use L'Hopital's rule. Remember, L'Hopital's rule says that what you do is you take the derivative of the numerator. So the derivative of 4 times the natural log of x is going to be 4 times, well, the derivative of the natural log of x is 1 over x. And then the derivative of the denominator. Well, the derivative of x cubed is 3x squared. Now we take the limit again, but since this is a little messy, let's clean it up first and then take the limit. This is really, the limit as x goes to infinity of, well, 4 times 1 over x is 4 over x. And then if we are dividing by 3x squared, we're really multiplying by the reciprocal. And the reciprocal is going to be 1 over 3x squared. This becomes the limit as x goes to infinity of 4 over 3x cubed. What is the limit as x goes to infinity of 4 over 3x cubed? Well, that's going to be 4 divided by infinitely large number, and that's going to be equal to 0. Recall from Calculus 1 that the limit as x approaches plus or minus infinity of a constant over x to a power, that would equal 0. Again, c here is a constant, and r has to be greater than 0. So c there is a constant, and r has to be greater than 0. But whenever you have the limit as x approaches infinity of a constant divided by x to a power, that's always going to be equal to 0. Number 6. Recall, always start with direct substitution. So this is the cosine of, I plug in a pi over 2. I have 3 pi over 2 divided by, if I plug in a pi over 2 here, I have the cosine of 5 pi over 2. Well, the cosine of 3 pi over 2 is 0. The cosine of 5 pi over 2 is 0. So this is indeterminate form again. It's 0 over 0. L'Hopital's rule says in order to evaluate this limit, what you need to do is take the derivative of the numerator. Well, what's the derivative of the cosine of 3x? Well, it's going to be negative 3 sine of 3x. Then what's the derivative of the denominator? What is the derivative of cosine of 5x? Well, it's going to be negative 5 sine of 5x. Let's clean this up before we try direct substitution again. We don't need those negatives, so it's a limit as x goes to pi over 2 of 3 sine of 3x over 5 sine of 5x. Plugging in that value of pi over 2, this is going to be 3 times the sine of 3 pi over 2 divided by 5 times the sine of 5 pi over 2. Well, the sine of 3 pi over 2 is negative 1, and the sine of 5 pi over 2 is positive 1. So this limit is negative 3/5. Number 7. The limit as x approaches 0 from the right of the square root of 1 minus x minus 1 all over x. Start with direct substitution. This is the square root of 1 minus 0 minus 1 all over 0, which is going to be the square root of 1 minus 1 over 0, or 0 over 0. Again, that's indeterminate form. We need to take the derivative of the numerator and the derivative of the denominator. If it helps you before you take the derivative, go ahead and rewrite this with its rational exponent, 1 minus x to the 1/2 power and then minus 1. Now, what is the derivative of the numerator? Well, the derivative of the numerator is going to be 1/2, and then 1 minus x, raise it to 1 less, negative 1/2, and then the derivative of the inside here is negative 1. This derivative of this negative 1 is 0, and we don't need to write that. Then what's the derivative of the denominator? Well, the derivative of the denominator is just 1. Let's rewrite this before we take the limit. We don't need this over 1. This guy here is a negative exponent. I'm going to move it to the denominator. I'm going to leave negative 1 in the numerator. 2 is already in the denominator. And I'm going to rewrite it as a radical instead of the 1/2 power, and that's going to be the square root of 1 minus x. Now, do direct substitution again. Negative 1 over 2 times the square root of 1 minus 0, well, that's going to be negative 1/2. So the limit as x approaches 0 from the right of the square root of 1 minus x minus 1 all over x is going to be negative 1/2. Number 8. The limit as x goes to infinity of e raised to the 2x plus 4 divided by x squared plus 4. First thing you do, since it's a limit at infinity, is think, what are you really looking at? Well, I'm looking at an e to the 2x and an x squared. So e to the infinity is going to be infinity, and infinity squared is going to be infinity. So you have infinity over infinity, and that is indeterminate form. Then you start taking the derivative using L'Hopital's rule. What is the derivative of the numerator? E to the 2x plus 4. Well, that's going to be 2 times e to the 2x plus 4, because the derivative of e to the u is e to the u times u prime. Well, the derivative of 2x plus 4 is 2 times e to the u times e to the 2x plus 4. What's the derivative of the denominator? Well, the derivative of x squared plus 4 is just 2x. These 2's will cancel, and you're really just looking at the limit as x goes to infinity of e to the 2x plus 4 over x. Still a limit at infinity, so we're really thinking what happens when I plug infinity into those leading terms. This is still infinity over infinity. It's still indeterminate form. Use L'Hopital's rule again. The limit as x goes to infinity of, take the derivative of the numerator. What is the derivative of e to the 2x plus 4? 2 e to the 2x plus 4. Take the derivative of the denominator. What is the derivative of x? 1. You don't need the over 1, so this is really 2 times infinity, which is just infinity. So that limit is equal to infinity.